All right, here in this video, I'm going to start talking to you about enthalpy. Enthalpy is a new unit that we're going to be using, a new kind of variable to talk about energy changes. Enthalpy gets the unit of H. Don't ask me why, but that's what enthalpy is. The unit of, or the variable for enthalpy is H. And enthalpy really is talking about the change in energy at constant pressure. And thankfully for us, this is what we're talking about most of the time. So all of the calorimetry type questions that we've been dealing with, like when we've been putting hot metals into water and seeing how the energy flows from the hot metal into the water, that is a change in energy. And it's a change, it's at constant pressure because we're talking about an open system. It's not like we've put the metal into a container and then close the lid on it. That would cause changes in pressure. But since it's open to the atmosphere, that's at constant pressure. So most of the time we're talking about just normal things that we can do in the lab, and that's a change in energy that we're going to call enthalpy. Usually we talk about enthalpy in terms of a delta H. That's the change in enthalpy. We don't usually talk about the absolute enthalpy of a compound, for example, but we talk about the change in enthalpy of a reaction or something along those lines. So when we are talking about it in terms of a reaction, we talk about the delta H. That's going to be the final enthalpy minus the initial enthalpy. So that's the same as we talked about with the delta T. So in the Q equals MC delta T equation, delta T was the change in temperature, and we talked about it being final temperature minus initial temperature. And that's the same thing going on here with enthalpy. Delta H is equal to final minus initial. When we talk about it really in terms of a reaction, the delta H of any reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. So let's look at an energy diagram. And in this energy diagram, this is energy versus reaction coordinates. And in this particular diagram, we have a certain amount of reactants and they have a certain amount of energy, and we're going to put this energy down here. After the reaction has occurred, our products have higher energy. So we connect them via a curve that looks like this, where the very tip top here is called the transition state. I'll talk more about this later, next semester, I think. But this is the transition state. And the change in enthalpy is from here to here. This is the delta H for the reaction. So this is an uphill reaction. Energy is required. So this is uphill reaction. Energy is required. So if we were in class, I'd probably do a clicker question for you right now, and I would say, well, if energy is required, is that an exothermic reaction or is that an endothermic reaction? When energy is required, that is endothermic. Endothermic energy is required in order to make the reaction occur. The reaction takes in energy from the surroundings. The surroundings get cold. So let's try to relate the delta H of the reaction for an endothermic process. So delta H is always products minus reactants. Let's just put in some random numbers here, okay? Let's say that this is 150. Let's say that the reactants are 50. The delta H then will be products minus reactants. That will always give you a positive value. So when delta H is positive, the reaction is endothermic energy is required. I really, really recommend that you start to get this into your head. I'll ask you about it a lot from now through organic too, if you have me for organic. When delta H is positive, the reaction is endothermic and energy is required. Let's look at the reverse. So, enthalpy, change in energy at constant pressure. We're going to look at the delta H for a reaction that's downhill. So here is a reaction diagram. Energy is along here, and the reaction coordinate is along this axis. So we're going to have a reaction where the reactants are high in energy and the products are low in energy. We connect them with a curve that looks like this. The very tip top is what's called the transition state. That's my favorite part. I guess the reason that I point this out is I really like transition state chemistry. This is actually where kinetics takes over, and I'm actually a kinetic chemist. And so this is why I keep talking about the top of this curve, because it's my favorite part of reactions is the kinetics. We'll do a lot more with kinetics in the second semester, so that's why I'm focusing on that. But for right now, we're talking about thermodynamics and thermochemistry. Thermochemistry is just talking about the change in energy from products to reactants. So this piece down here is the delta H of the reaction, the change in enthalpy. So again, delta H for a reaction is equal to enthalpy of the products minus enthalpy of the reactants. Products minus reactants, final minus initial. Again, let's go ahead and just put some numbers here so I can show you. So in this case, we're going to say our reactants have 150 energy. Our products have 50 energy. So the delta H for this reaction would be 50 minus 150. That gives you a negative number. So in this case, this is an exothermic process. It is exothermic because energy is released. When you go from less stable to more stable, energy is released, and that is exothermic. So when the delta H for a reaction is negative, the reaction is exothermic, energy is released. So again, I really recommend that you start to get this in your head. It's never going to be anything but delta H is negative, exothermic, energy released, or delta H positive, endothermic, energy is required. So I really recommend that you start to get these linked together in your head. Let us talk about the units for delta H just real quick. The units for delta H are typically given in terms of kilojoules per mole. So you know what a joule is? That's kilojoules, so that's a thousand joules is a kilojoule per mole, and that's typically the units that we're given for delta H. Those are going to become important in the next video. All right, next up, let's talk about changes of state. Changes of state are when, for example, you have water as a liquid becoming water as a gas. So that's an example of a change in state. You went from the state of liquid to being in the state of gas. So this is where I would take a second and I would ask you, what is this process called? This is evaporation. If no heat is given, then it is evaporation. If heat is given, then it's boiling. And then I would ask you, do you think that this process is endothermic, energy required, or exothermic, energy released? This is sort of how I think about it in my head. We have a liquid becoming a gas. Liquid is low in energy compared to gases. I talked about that previously. Gases have a lot of kinetic energy. Liquids have some. They're more than solids, but they have less than gases. So if you connect these two things, you can see it's an uphill process. The change in enthalpy for the reaction is products minus reactants. It is an uphill process, so this is energy required, endothermic. For an endothermic process, the delta H should be positive. This is given a specific name. This is called the delta H of vaporization. That is the quantity of energy required to convert a liquid to a gas. That's the delta H of vaporization. I wish I had it for you. I don't have it written down for you right now, so I'll have to give it to you when we actually deal with it in a problem. Interestingly enough, you can reverse the process. You can have the phase change from water vapor to liquid water. This process is called condensation. The delta H for this particular reaction is equal to the negative delta H of vaporization. This is an exothermic process. It's exothermic because, again, if we look at the energy diagram, we're going from a gas to a liquid. That's downhill in energy. Gases are high in energy, liquids are lower in energy. This downhill process is exothermic. For an exothermic process, the delta H is negative. You can see it's the exact same reaction as the evaporation reaction. It's just reversed. So the delta H for this process is the same quantity as the delta H of vaporization, just the opposite sign. So again, I've been sort of focusing on these signs for all of thermochemistry. They're very important. So liquid to gas, delta H of vaporization, positive. Gas to liquid, delta H of vaporization, but negative. Let's look at another change of state. This is the delta H of fusion. The delta H of fusion is when you have water as a liquid becoming solid water. Again, let's figure out if this process is endo or exothermic. Liquid is high in energy, solid is low in energy. So that's the liquid, that's the solid. That's a downhill process. A downhill process is exothermic. So this process, the delta H of this reaction, is negative delta H of fusion. The real definition of fusion, I apologize, I kind of skipped ahead here. The delta H of fusion really is when a solid becomes a liquid. So my apologies here. This is the negative delta H of fusion, liquid to solid. The actual delta H of fusion is solid to liquid. Water as a solid becoming water as a liquid. That's positive. That's endothermic. So let me give you the official definition of the delta H of fusion. It's the quantity of energy required to convert a solid to a liquid. That's the delta H of fusion. And it's endothermic because energy is required to melt something. Again, the units on these are kilojoules per mole. The last thing I want to say about changes of state is that changes of state are isothermal. Okay, what I mean by that, iso means stays the same. Thermal means temperature. So stays the same temperature. So if you have, let's see, what do I want to do here? I'll do some solids. So here's an ice cube. And we're going to add some energy to it, and eventually the ice cube melts into a puddle. The temperature of the solid ice is 0. After all of the solid ice melts, the temperature of the water is still 0. All that's happened is that it has undergone a phase change. All of the energy is put into the ice cube to go and cause the ice cube to go from a solid to a liquid. None of the energy that goes into the ice cube relates to a higher temperature until all of the liquid is melted. All of the solid becomes a liquid. So that stays the same temperature. You can add energy into the ice and it will undergo a phase change. It's sucking in that energy, and it's, you know, causing intramolecular bonds to break, and it's causing the phase change from solid to liquid. But the temperature is staying the same. So changes of state are isothermal. The same thing happens when you go from a liquid to a gas. Again, it's a phase change. I'm going to put a lid on this so that we can see what's happening here. This is liquid at 100 degrees Celsius. It's going to undergo the phase change to become a gas. That gas will also be at 100 degrees Celsius until every single last bit of the liquid has become a gas. It stays the same temperature even though energy is being added. The energy that's added goes into the phase change first before the temperature changes. That's going to become really important for the next concept.